Afternoon, everybody. Thank you very much for organizing this very interesting meeting and for inviting me. I hope you can hear me. Yeah? So I switch to full screen now, if I can. Whoops. And I hope you can see it, and I will try to advance with my mouse. Yes, so I will talk about very dense plasmas, quantum plasmas, and an interesting property of these systems, which is the momentum distribution of these plasmas. And this momentum distribution differs from classical plasmas quite substantially. And we have developed some first principle simulations to describe this very accurately. So this work is together with Alexei Filinov from my group. Let's see if I can point. And with Tobias Dornheim, a former PhD student who is now at CASAS in Görlitz. So what is the talk about? So the momentum distribution is in thermodynamic equilibrium is quite well known. If you first look at classical plasmas, then you know that it's a Maxwellian, and a Maxwellian distribution, maybe I can write it here. A Maxwellian distribution decays exponentially as a function of momentum. So this is n of p. I hope you can see it. Goes like p squared over 2m kt. So that would be the classical case. No? That's an ideal plasma. But if you have interactions in the system in a classical plasma, then you would write the total energy of the system of all particles. It has some potential energy parts, p, momenta of all particles. So this is additive. Yeah. So this is the sum of kinetic energies. Let me write it as a function of p, and another energy term which depends on all the coordinates of all the particles. That's additive. Right? If you now write a distribution or a probability that our particles are in a state R and P, then this is a Boltzmann factor, a to the minus beta h p plus h r. Yeah, and with beta I denote 1 over kt. Yeah? So in a classical case, if you now have interactions, this is given by these guys here, then the probability to observe some momentum state is independent of the interactions, because you just integrate the R-dependent term away and you are left with that. Now, what about quantum plasmas? Again, in an ideal quantum plasma, we have an exponential decay. In a quantum plasma, we have an exponential decay, which is given by the Fermi function, which is 1 over 1 plus, and then we have p squared divided by 2m over kt, if it's just kinetic energy. So for large p, again, it decays exponentially. Yeah? But now comes the crucial point. The crucial point is that if we now turn on interactions, if you now turn interactions in a quantum system, again, we have this total energy. Now I have to write this total energy as an operator. I have here an operator, I have here an operator. And then you will observe that in a quantum plasma, these two operators do not commute. So if I write a commutator, HP, HR, is not equal to 0. This means I cannot integrate this R-dependent term away. So the momentum distribution function in an interacting system will always know something about the interactions in the system, in contrast to the classical plasmas. Yeah, so just keep this in mind. So this non-commutation of these two terms in a quantum system should lead to a different dependence of the momentum distribution function, especially for large p. And this is on my next slide. For non-ideal quantum plasmas with interactions present in the systems, there is not an exponential decay. And there has been some predictions long time ago already by these guys that there will be a polynomial decay with the 8th power of the momentum. And the question we put to ourselves was, can we verify this? Is this true? What are the coefficients? How does it depend on the temperature and on the density, etc.? And if it would be true, then it could have some implications. Why could it have some implications? So if you again plot this distribution function as a function of p, and let's say look at logarithmic of this distribution function, if I would have for large momenta and exponential decay, it would vanish very fast. If I would have not an exponential decay, but a slow decay, then it could matter, let's say, if I have processes which require energetic particles with high momentum, and all these particles contribute to some processes like impact ionization, fusion rate also, then all these particles which have an excess of some threshold, p threshold, and all these particles contribute to, let's say, a given process, then an exponential decay or a non-exponential decay. So the difference between the curves, the areas of these curves can matter, even if the absolute numbers are small. So that's the motivation for this work. And we developed some quantum Monte Carlo simulations, which I will briefly explain. The results are given in that paper. And Tobias has written another paper with some more results. Let me just go back to the start and point out one thing. If you are interested in the talks, the PDF is available at my webpage. So there will be some more details in this PDF, which I have to skip over. Okay, let me continue and motivate why these systems are important. So we are looking at dense quantum plasmas. In some cases, this is called warm dense matter, which has many important applications. The first is astrophysics. So the interior of giant planets or of dwarf stars is described by such matter, which has density in excess of solid state density, but which are not too hot. So it's not hot dense matter, but warm dense matter. Also, many of the recently discovered exoplanets should fall into this category. So for astrophysical applications, to understand in particular the behavior of the electrons at these quite complicated conditions is important. Okay, also in the laboratory, such matter is very important. An example is shown on the top right. This is just a scenario of inertial confinement fusion. In a very simplistic way, you shine laser on a deuterium-tritium pellet. As a laser is reflected and generates a shock wave, which goes inside, compresses the matter such that two hydrogen atoms can fuse to helium, for example. But this is not the only application of such intense lasers. Let me go to the next. The biggest facility is the National Ignition Facility at Livermore National Lab in California, which you see here, which is a gigantic facility in order to produce these high laser energies which are needed. This is now also broadly used for basic research. For example, they really have started a big program to study matter under extreme conditions, like matter inside of such planets, but also matter, let's say, inside of white dwarf stars. And in that paper here, they have achieved densities or pressures on the order of 500 megabars, which is close to conditions in white dwarf stars, and they really could diagnose this. So there's a very interesting developments now. You can really now do many astrophysical systems in the laboratory. This is also a challenge for theory because they have quite accurate, on the order of 5% accuracy data for the equation of state. So this requires quite accurate theory in order to reproduce this. But of course, the fusion is still the main and the most exciting application of this. And I want just to show one of the most recent shots, which is described here. A year ago or so, they produced a record shot, and a few more after that, which achieved a self-burning plasma, which has not been achieved in tokamaks so far. So they have achieved a burning plasma, and they are saying that they are quite close to ignition. So this could happen anyway, anytime soon. So it's quite exciting to be, let's say, to follow this, and also for a theoretician like myself and you, it's an exciting area to develop accurate modeling of such systems. Okay. There are more facilities, of course. There's a big progress in many countries now. Except from the laser facilities, there are free electron lasers, which are also used to test these systems to compress matter. There are ion beam facilities under construction in several countries, which are also quite efficient to compress matter and to study these systems. So that's definitely a hot topic. Now let's think about theory. How would we model such systems? First is to understand what are the conditions. And for that, you need to understand what are the parameters and what are the relevant dimensionless parameters. So here's a temperature density plane for the warm dense matter. Here's density. So that would be the typical density of normal metals, for example. And warm dense matter is this bubble here, which is in a range of such densities and temperatures. And now if you construct these dimensionless parameters, which is important, the first is a density parameter, or you can call it a coupling parameter. This is the mean interparticle distance in units of the Bohr radius. So 1 would be here. If you compress the system, you would have here the line 0.1. Here would be the line 10. And what we know from quantum systems is that if you compress the system farther, the system becomes ideal. It goes towards an ideal Fermi gas. In a classical system, this is different. So the second parameter is the dimensionless temperature. That's the degeneracy parameter, theta. So for large, theta larger than 1, we have a classical system. And so above this line, high temperatures, classical plasma, and below we have a quantum plasma. Yeah, and this warm dense matter comprises both situations. So it is in a range where these parameters are on the order of 0.1 to 10 maybe, and the same for RS. Which means that usually we don't have a small parameter, so perturbation theory does not work. And you need either good models or reliable simulations. And this is what we have done. Of course, also the ionic component is important. If you have, let's say, at these ranges, typically the ions are classical. So here's the energy scale for the ions describing the kinetic energy is the temperature. For the electrons in a quantum regime, it's typically the Fermi energy, which is a kinetic energy range. No? So for classical plasma, this parameter is also on the order of 1, but it can also be much larger at large density. No? Okay, that's warm dense matter, which is quite a complex system, as you understand. Coulomb interaction is very important, of course. Then quantum statistics plays an important role, and you all know that there's a big difference between bosonic and fermionic particles. We are mostly concerned with fermions because the electrons are the most important quantity. They are fermions. And for fermions, we know that we cannot put 2 fermions at the same energy level here. So if you fill up n electrons in such a system, you have a very big increase of the energy with the number of particles or with the density. And this has to be taken into account. And of course, typically, as I said, we are not in the ground state. So we also need to take into account finite temperature effects. And here again, I plot a distribution function, but now not as a function of the momentum, but as a function of energy. And as a function of energy, this is always a Fermi function, no matter whether the system is interacting or not. It changes only if I plot it with respect to the momentum distribution. Yeah? And here as a function of temperature, at low temperature, this is a step function. And if we heat the system, more particles move up to higher energies. Okay, all these effects have to be taken into account. And as I said before, we can practically not describe the whole system with all the components self-consistently very accurately. The most successful approach to do this is density functional theory, but the accuracy is quite limited. So it's very important to have some, let's say, other complementary systems, methods which allow to treat the most important components, electrons. And this brings me to the next topic. So for this reason, we looked at the electronic component, which can be successfully modeled as a uniform electron gas with a neutralizing background. And if you understand the problems of this uniform electron gas, you can plug these results into a full two-component simulation like the density functional theory and describe the whole system. So we concentrate on the electrons and recall just the developments which took place in the 80s. In the 1980s, people started to look at the ground state properties of these systems and used Monte Carlo simulations to describe what is called the exchange correlation energy, which is the addition to the ideal kinetic energy. So it's a difference between the total energy minus the ideal kinetic energy. So this describes quantum exchange effects and electronic correlations. So for this, quantum Monte Carlo simulations by Zeppeli and Alder were derived and which were quite accurate and which allowed to parameterize this exchange correlation energy, which then became input to density functional theory, which is today the workhorse of atomic, molecular physics, chemistry, material science, based on this quantum Monte Carlo data, and also it's starting to become applied to warm dense matter as well. Okay, but now I said that we need a final temperature data for warm dense matter, so on the order of the Fermi temperature. So we have to go away from the total energy in thermodynamic equilibrium. At those temperatures, the key quantity is the free energy. And the exchange correlation free energy, similar to that equation, is then the difference between the total free energy minus the ideal free energy. So in the small f just means the density per particle or per volume. Huh? Okay, and our goal was then to develop quantum Monte Carlo simulations now for finite temperatures and to compute this exchange correlation energy. And at the end, I will show how we apply it to the momentum distribution. So here are the results or the method, just a brief idea what we do. We do develop path integral Monte Carlo simulations for fermions, which tries to avoid this non-commutation of potential and kinetic energy. And how you can avoid this non-commutation, you have to map this system onto a high temperature system where the properties will be almost classical. And this is represented here. So this chain of dots, beads, represents a single particle, which is mapped onto a system of high temperature factor, so to say. So all this is now one electron. This is a typical coordinate. And the path integral maps each particle onto some single trajectory or path, which is random. Yeah? So that's a well-controlled procedure, which is due to Richard Feynman, and which we have further developed. There's a problem, and the biggest problem here is the fermionic exchange due to the Pauli principle, fermionic nature. Particles are not only given by such trajectories, but particles, since they are indistinguishable, can be represented by such crossing trajectories. And we have, for two particles, we have such identical trajectories, we have crossing trajectories, because all exchanges between the particles have to be taken into account. And for n particles, these are n factorial exchanges. So that's a representation of a two-particle exchange in the path integral picture. And this can be done quite successfully for bosons. It works exactly the same way. For fermions, we have a key problem. For fermions, we have this sign factor. And this sign factor tells us that such a pair permutation of two particles will enter with a negative sign. And of all the n factorial permutations, 1/2 will have a positive sign and 1/2 will have a negative sign. This is related to the fact that the n particle states of such systems also will change their prefactor, their sign, when we exchange two particles in such an n particle wave function. So this is just to be remembered. For fermions, we have this sign alternating contributions to the partition function, which is just a trace over the probability density. And this leads to the fact which is called a fermion sign problem. Just let me show you a snapshot of such simulations. As I said, each particle is represented by such a set of beats, such a trajectory. These are random, and during the simulation we average over such random configurations, and this gives us something like the wave function, more or less, with a correct extension of the particles in 3D space. No? And exchanges can also be seen, then two particles overlap, more or less. No? So we generate all these trajectories by the standard Metropolis algorithm. So this is not difficult, can be quite easily developed. And but as I said, this sign alternating contributions makes this difficult for fermions. This fermion sign problem is currently unsolved. And the consequence is the following, that if we lower the temperature, then the mean sign, which is just the average of this expectation value of the prefactor, goes down exponentially. You see this exponentially going down on the log scale, linear scaling, when the temperature is decreased. And the rule of thumb is, if the sign falls below something of 10 to the minus 3, simulations are not efficient anymore. So this is now a limiting situation for fermions. For bosons, we don't have this problem. So for 10 to the minus 3 or above 10 to the minus 3, we can do the simulations. So for small systems and for not too low temperature. And okay, now if you apply this to warm dense matter, this fermion sign problem limits standard simulations to not too high densities. So here is a density parameter. So this was the mean interparticle distance, which means that the density increases here to the left on this scale, and this is this scale temperature. Here's this warm dense matter again. And standard simulations, PIMP simulations, are limited to not too low temperatures and not too high densities. So they can be done here to the right of this. So there have been some workarounds this limitation. This is called fixed node approximation. With a fixed node approximation, one eliminates these negative contributions approximately. So this has allowed to go these guys with this RPIM simulations approximately to this green line, but they could nevertheless could not go to higher densities. So we followed a different route. We wanted to avoid these uncontrolled approximations. And we developed two independent simulations. One is a completely new approach, which is called configuration PIMP, which does not work in coordinate space, but it works in Slater determinant space, which has the advantage that we can treat high density systems exactly. Excuse me, I have to take a sip. So I will show a sketch of the method in a minute. So this CPIMP can work along this shaded area for high densities, but we also have a sign problem. This is a hard problem, but it appears if we go to lower densities, higher RS, so somewhere here we can still do simulations, but here's the end. Yeah, but this is of course a breakthrough, because this entire area was not accessible before. And now the interesting thing is you can combine it with a second approach, which is similar to standard Monte Carlo. It's a slightly improved method in various ways, but it also works in coordinate space. We call it permutation blocking, Parsnett-Grad Monte Carlo, and it works along this horizontally shaded area. So here it is exact. It can still we can still do simulations here, but not at too low temperature. Yeah, and the nice thing is that both of these methods have a fermion sign problem, but in complementary areas of the phase space. One has a fermion sign problem here, and the other has a fermion sign problem here. And now combining this has allowed us to achieve really the first ab initio data for the electron gas at warm dense matter conditions. And here is an example of the exchange correlation energy, which we plot here. Here's the RS parameter again, and here are two temperatures. And what I show here are these restricted particle Monte Carlo data with this uncontrolled approximation. This is given here, and which fail or stop here, but they also do not contain the correct asymptotics, because this exchange correlation energy is known to be the leading term contribution is the mean field energy, Hartree-Fock energy, which has a limit. It goes like 1 over RS. So if I multiply it with RS at low RS, it should go to a horizontal line. And these curves do not describe this. And let me show you our results. These are the CPIM data, which are accurate for high density, and you see the correct asymptotic here. Here the sign problem kills us, so we have to stop here. But the second method, which is this permutation blocking, comes from the right. These are the crosses, and nicely merges within error bars into these simulations. So we have really now an exact approach to these systems, which we can use to connect, combining two methods, but the low temperatures are the limits. So something like half of Fermi temperature is the limit where we can still connect the curves, but below that we have had to use other, let's say, extrapolations, for example. So that was the status, I would say, 5 years ago, where we first published these data for the thermodynamic quantities. And this was quite successful and was also recognized by the American Physical Society, which who gave us a Thorson Award last year for these simulations. And in collaboration with two colleagues from the UK and one from the US. And after that, the work continues in quite a number of interesting directions, which I only mention here. We now go away from the thermodynamics. So we have approached transport properties using linear response theory. So we computed the dynamic structure factor. We computed the dielectric function. Ab initio data for the plasma dispersion of the electrons are available, and you find this in these references, and also the momentum distribution, which is the topic of my talk. So let me now switch to the momentum distribution. So I already said why it is interesting, and that we expect for large P to have this 8th power of P decay in contrast to an exponential decay. And so we looked in detail at the earlier works, how the people did the calculations. So the analytical work was first done for 0 temperature, then came some extensions to finer temperature. And one should also mention this is not only important for plasmas, it is also important for other systems like cold atoms, which are also in quantum degenerate states, but there the interaction is different. Typically, they have something like a contact interaction instead of Coulomb, and there is also an algebraic decay, but with a different exponent. Okay, a main result which has been found before by these people was that you can relate the asymptotic at large P of the momentum distribution function to another quantity, which is a so-called on-top pair distribution function. This is the probability to find two electrons with opposite spins at 0 distance. Yeah, two particles with opposite spin can in principle sit on top of each other quantum mechanically. And the prediction was that this relation contains the 8th power of the momentum, but the prefactor is essentially given by this value of this probability, this on-top pair distribution, which I will also show. And with quantum Monte Carlo, we can compute the on-top pair distribution, and we can compute the momentum distribution separately, which is quite interesting. Okay, now let me come to our second approach. This is this configuration, path integral Monte Carlo, which works at high densities. This is the Hamiltonian. So if you are familiar with second quantization, it's easy to understand. So these are operators which create or annihilate a particle in some single particle orbital. So if you think about the harmonic oscillator, for example, particles can sit on discrete levels. So discrete levels are shown here. These are these orbitals, and these operators annihilate an electron there or create an electron there. Then if the particles interact, then the interaction, the Coulomb interaction can be described by such an expression with 4 such operators. And if our system would not be interacting, then in this picture here, particles would just be sitting on their orbitals and not change their orbitals. So we have here the sketch for 3 particles which sit on orbitals 0, 1, and 4. And if they would not be interacting, this picture would just contain straight lines. 3 straight lines. But the interaction leads to the fact that they will not remain in their orbitals, they will be pushed out due to the interaction. And this is sketched here, so this particle will go up, and another particle can go up, they can go up simultaneously, etc. That's a random process. And our procedure, our CPIM procedure just takes into account all these deviations from the straight lines, from the ideal system, all these, we call this kinks in these paths in configuration space. And using the Metropolis algorithm, we evaluate these, let's say, interacting states, so to say. Okay, this procedure works. It's more complicated than the standard coordinate space PIMP, but as I said, it gives us access to the high densities. And if you want to compute some observables like the density matrix, or this is, you can call it distribution function, this Ni, if we work in a momentum basis, then this function would give us a momentum distribution. We can compute it if we know the partition function, the normalization of the density operator, just by differentiating with respect to this prefactor. And then there's an explicit result available, which is quite simple. I will not go into this here in detail. For the on-top pair distribution function, we need a 2-particle function, which is an expectation value of such 4 operators, which we also have directly available. If we have the partition function, we just differentiate with respect to such a matrix element. And that's the final result which you get in CPIM for this on-top pair distribution. This is just such an expression. I only show this in order to show that it can be really explicitly written down, and depends on the length of the simulations, how accurate this is. And of course, we cannot avoid the sign problem. Okay, let me show you maybe the most important result. This is CPIM result for the momentum distribution. Now, momentum is K in units of the Fermi momentum. So what do we know? We know for 0 temperature, for a non-interacting system, the distribution function is just a step function. So that's the log scale here. What is a step function? This would be just a constant value. Occupations are 1 up to the Fermi momentum. Here's the Fermi momentum. This is 1. This is the step. Yeah? Now, if you have no interactions and increase the temperature, then we have a Fermi function. I showed this in the beginning. And with no interactions, it's an exponential decay. And are these dashed lines here for different temperatures. So the lowest temperature here is 1.5. This is this one. And you see this linear, which means exponential decay. And with increasing temperature, this exponential decay goes to higher temperatures, higher momenta. This is the ideal Fermi gas. Now we turn on the interactions, and with the interactions, we do not have this commutation between potential and kinetic energy, and we do not have consequently the exponential decay. And this is what you see. This is the result of the simulations here. This is a slower p to the -8 decay. And you see some noise here in the simulations, but if you look at the scales, you see this is -11. The population here is on the order of 10 to the -0. This is order 1. So what we get in these simulations is something like 11, 12 orders of magnitude accuracy of the simulations. So this is an absolutely amazing result, which is only possible with the CPIMP, and which gives us the possibility to resolve this tail very accurately. And here's the Fermi edge, so we can go to something like 15 Fermi momenta. Yeah, but as I said, CPIMP we can do for high densities, so small values of RS like 0.5, for example. So here's a second representation where we fix the density. So here's, no, sorry, I fix the temperature here, which is 2 in the right figure. But we vary the density again. The ideal function, ideal Fermi function again is shown here, the step function. And this is the ideal Fermi function if we neglect interactions. And these are again the simulations. Red, weak coupling, high density, blue, moderate coupling, lower density, and we see the same trend. Yeah, so these data are available for quite high density, RS smaller than 1. Okay, and then we did in this paper here quite further analysis. So we looked at the asymptotics here for large K, compared it with the ground state. These are the green curves. And we also compared it to this analytical prediction with a on-top distribution function, which we computed separately. And this prefactor here was a fit to this pair distribution function asymptotic. And as you see, this asymptotic is accurate. The simulations really go into this red curve. Of course, the ground state is different because this was a fit to a finite temperature, theta equals 2 asymptotic. So we can confirm this, and we can really now also compute the prefactor, which is known from the analytical side or only in the asymptotic for very large K. Here we see it for finite K.
No, Professor, you have 3 minutes more.
Okay, then I will go a little bit to the end. Another interesting observation is to see how this changes if we compare K resolves the distribution for small k. There are some interesting results, and I skip this. And I skip this. Here are some results for the pair distribution function, how it changes as a function of temperature. And these are the results for very large RS. So this we cannot do with CPIMP. This is done with permutation blocking PIMP. And here you have something like RS2 to RS50. And you see that with very large RS, this means very strongly correlated electron liquids, the distribution is strongly is decreased at small momenta. Okay. And the final thing what I wanted to show is we also have started to extend it to two-component plasma, electron-proton plasma, and compared it to electrons in a hydrogen atom. So in hydrogen atoms, this would be the 1s distribution wave function. You can also compute the momentum distribution. It's a known result. It's interestingly also, here's a p, also decaying like the 8th power for large momenta. And the question was now in the simulations, can we reproduce it? Here's again momentum distribution function for a given value of the coupling strength. Here's the uniform electron gas result, the one component result. The ground state wave function is this green curve. And now you see simulations for hydrogen with our simulation, quantum Monte Carlo simulations for 3 temperatures. And for lowest temperature, here we really can nicely reproduce the 1s function. But for higher temperatures, of course, we see deviations because we have excited states present in the system. So with that, let me just conclude so we have time for some questions maybe. So we have computed the momentum distribution function, which can be important for a number of interesting physical processes. We have highly accurate results available for the first time. And what we want to do is to compute a number of additional quantities, which describes the density of states of these plasmas or warm dense matter. But this is work in progress. Okay, so with that, I stop and will be happy to take your questions.
Yes, please raise your hand. Any question from the participants? I don't think actually the description was quite itself clear. You started from the very basic difference between the classical and the quantum plasma and the distribution functions. So I think it was a very clear-cut presentation. There's a question from Dr. Kavita. Dr. Kavita, you can ask.
Good afternoon, sir. Actually, I missed the initial part of this presentation. I'm very sorry for that. Can you please tell me what is the basic difference between the quantum electron or in general what we use in the plasma?
Okay, so I go back to the initial slide. So I said at the beginning that, of course, the momentum distribution is well known for classical plasmas. It's a Maxwellian, huh? Right? And it's a Maxwellian with interactions included and without interactions. Yeah, and for quantum plasmas, this is not the case. For quantum plasmas, an ideal plasma has a Fermi function, which decays exponentially, like I sketched here. Yeah, but if you have interactions like we have in real plasmas, Coulomb interactions, so it is not longer an exponential tail, but the tail can be shown to be going with the power of the momentum, with the eighth power of the momentum. And that is a pure quantum effect. Yeah, and the goal of this talk was to verify this prediction with computer simulations, and this we could do. Yeah? So if you are interested in the whole talk, you can just download it from my webpage. No?